Okay, so I'm going to consider very simple parabolic equation, which is a heat conduction equation. Parabolic PDE, very simple partial differential equation, parabolic partial differential equation, that is heat conduction equation, which has heat conduction equation, which has this form. K multiplied by second derivative of t with respect to x is equal to second derivative of t with respect to time. So this equation describes one-dimensional heat transfer. It's a situation when there is a heat transfer in one dimension. For example, you have this, let's say, thin object, which is connected on both sides, and this has a length of L. Okay, let me introduce an x-axis to describe that. So this is 0, x equal to 0, and this is x equal to L. And this is my object, thin object, like last time. And this conducts heat. I have boundary conditions on both ends. I have some condition. Let's say I have some fixed temperature here and some fixed temperature there. And the equation which describes how heat transfers from one side to another is given by this equation. Okay, so the solution of this equation tells me the temperature as a function of x and as a function of time. The solution of this equation tells me temperature as a function of x, which means at any point here along x-axis, and also as a function of time, which is how it changes with time. Initially, it may be one value, but after some time, it may be another value, so it tells me that too. Okay, it's a two-dimensional function. T is a two-dimensional function. And this guy describes one-dimensional heat transfer. Okay, so if you have more than one dimension, one space dimensions, okay, if there is a heat transfer also in this direction and in that direction also, then that equation has a different form, of course, and that form, let me just write, will be this: k second derivative of t with respect to x plus second derivative of t with respect to y plus second derivative of t with respect to z, and all of that is equal to second derivative of t with respect to time t, where t is the temperature. Okay. So we need to solve this equation. Okay? Let me just remind you, in order to solve this equation, before we talk about any methodology of solving, we have to figure out what we need here. First, of course, if we just think intuitively, in order to describe how temperature changes with time, we should know what was the temperature at the very beginning, right? Without that, we cannot solve it in principle, which means we need initial conditions. Initial condition. So let's say t at any x at t equal to 0, okay? At t equal to 0, t as a function of x, and let's say that is given me with a function t0 of x. This is given. Initially, I know what was the temperature. That's an initial condition. Second, of course, in order to solve or in order to determine what will be the temperature in future, we also need to know what are the conditions at the end of this object, right? Here and here. Which side is hot? Which side is cold, for example? How much heat is flowing in? Things like that. That is boundary condition. Boundary condition. Boundary condition. Okay, on the right-hand side, t when x is equal to 0. So this right-hand side corresponds to x equal to 0. As a function of time is equal to, let's say, t0 of t. So this is my first boundary condition. The boundary condition itself can depend on time. It doesn't need to be fixed in time. For example, if you are considering solving this equation for this room, the temperature inside this room depends on what is the temperature on the walls. And that can change, right, during the day, for example, during one day. Okay, so this is a condition on this side. We also need a condition on that side. And let's call it t at x equal to L. L is this point. And t is equal to, let's call it TL of t. TL of t. Okay, so I have my initial condition and boundary condition. Now, problem is we have all the information we need in order to solve this problem. Okay, one more thing, of course, we need the value of this coefficient, right? This is a coefficient which describes how fast heat is conducted. We also need to know the value of that, otherwise we cannot solve it. Once we provide all of that, value of k and initial and boundary condition, now we can think about solving it. Okay? So in order to solve it, I'm going to use, as we discussed last time, finite difference methodology. Finite difference method. And as we mentioned before, the idea behind finite difference method is that instead of finding a solution at every point at any time, instead of finding this guy as some continuous function of x and t, instead we learn, not learn, we look for the solution at some specific values of t and some specific values of x. Okay. In other words, we discretize both x and t variables. Okay, and we need a solution at some discrete values. All right. In the very simple case, those discrete values are equidistant, at equal distance from each other. So xi, let's call it xi. Index I means which one I'm talking about, which point I'm talking about. I ranges from 0 to some n plus 1. I multiplied by some delta x. Delta x is distance between these 2 points. So I ranges from 0 to n plus 1. So this point, boundary point, corresponds to x0, and this point, the last point, the right boundary, corresponds to x n plus 1. I equal to 0 and I equal to some n plus 1 are boundary points. Okay, and when I ranges from 1 to m, are interior points. Are interior points, and that's exactly what I need. I need t at those interior points. At this I equal to 0 and I equal to n plus 1, I don't need, because this point I equal to 0 and this point I equal to n plus 1. I have boundary conditions. Boundary conditions are given. Okay, I'm assuming that I know the temperature at the boundary. This is not the only way. As you know from previous lectures, that boundary condition can be given. For example, instead of the values of t, what we may be given what? Can you remind me? Derivative of t, right? For example. So for this simple case, we assume that we are given the value of t. So I know t here and here. Okay, very good. Now, next thing is, this is a discretization in space. So I look for the value of t at those points. This is not the end of the story. We also need to discretize time. Okay, let's call it TL. TL is some integer variable L multiplied by delta t. So we also have to discretize in time. Initial value is t equal to 0. My next time will be t equal to delta t. The time afterwards is 2 delta t's. So I am dividing my time variable into a set of equidistant points. 0, delta t, 2 delta t, and so on and so on. So L ranges from 0 to some n, such that when L equal to n is the last time I want. I want to solve from t equal to 0 until this tn. All right, so this is discretization in time. So I need t at xi and tl, and I call that variable til. All right, so this is my grid. This is my finite difference grid. Now let's start building a methodology for solving it, starting from the simplest method. Okay, so I want to solve this equation. Second derivative of t with respect to x multiplied by k is equal to first derivative of t with respect to t. All right. So in principle, we have to discretize in space and time. Okay, first I will talk about the discretization of this variable. Okay, this variable. I want to discretize that first. Okay. So dt, dx at point I and L, I will use very simple forward formula to discretize this, like we did last time. T L plus 1 I minus T I L over delta T. All right? Okay, so now, let me put this discretization here, this finite difference representation of this guy here, and see what I get, okay? So if I put this guy here, I will have T L plus 1 I minus T L I divided by delta T is equal to K, second derivative of T with respect to X at the same point L and I. Okay, let me find this guy out of that. T I L plus 1 is equal to T I L plus K d squared t dx squared at point L and I multiplied by delta t. And we have to appreciate one aspect of this formula. This is the most important formula. This is a very important formula. Does this remind you of anything? Does this formula remind you of anything? There is a very important condition. And what is this? What is that? It's integral. Which integral? Okay, so I'm going to write something on this side. So let's, for the moment, let me write a, on this side, let me write a system of ODEs, okay, system of ODEs. Okay, today we are discussing partial differential equations, but for the moment, to see a connection between this and something different, I'm going to write a system of ODEs, okay? So let's suppose that I have a system of ODEs. dy dx is equal to some f x y, okay, where y is a vector of unknown functions. It's y1, y2, and y some n. Okay, these are my unknown functions. All right. All right. So if I apply Euler's formula to this system, what I get is yi plus 1 is equal to yi plus f at xi yi multiplied by h. So this is the application of the Euler's formula to a system of ODEs. I have a system of ODEs of order n. I have n unknowns. These are my unknown functions. All right. Okay, now let's look at here. Let's look at here. So here, we are going from L to L plus 1. And here I have the step in the unknown variable where I go from TL to L plus 1. Plus multiplied by this guy. This is a function, the value of which is given at point L, All right, for the moment, let's ignore this I. Let's just look at the variable L. I'm going from L to L plus 1. Here I have a function which depends on L, and here I have a previous value. Doesn't it look like this? Doesn't it look like this? Here I go from I to I plus 1. And here I have a function where I have the value at yi and xi. The same thing here. Ignore this index I. I'm talking about index L here. I'm talking about only solving in time for the moment, right? Going from time L to L plus 1. I go from L to L plus 1. And here I have something which depends on L. So this is the Euler's formula then. This is Euler's formula as applied for time discretization. But we can view that, very importantly, we can view this as application of Euler's formula to systems of ODEs. Why? Each di, each of these i's correspond to one unknown function. This is how you can look at it. Okay? So these ti's are unknown functions. And for those ti's, you are applying Euler's method. And you can view it as a system of ODEs. Okay? You can view it as system of ODEs. System of ODEs. Each of I would correspond to these different unknowns. So that's a very important insight. And we're going to use that insight in the following. All right. So I applied Euler's formula. Now, the only thing left to do is to put the discretization of this term. Okay, we can use a very simple term like we did last time, which is a centered formula. We can use a centered formula to express this guy. L and I is just T L I plus 1 minus 2 T I L plus T I minus 1 L divided by delta x squared. All right, so if I put this guy there, what I get is TL plus 1 I is equal to TLI plus that guy, K delta T over delta x squared, T I plus 1 L minus T 2 I L plus ti minus 1 L. Okay, so this is the formula. After we discretize both x and y. Okay, let's try to draw this guy. Let's try to draw what this solution means. We will draw space and time diagram, so to say. We'll try to see the solution, how solution evolves in space and time. So let's say that this is my x-axis, this is my t-axis. So this is x equal to 0, and this is x equal to L. So these are my discrete points. And this point corresponds to t equal to t0, which is equal to 0. And let's say that this is, after some delta t, here t equal to t1, which is equal to delta t. Okay, so from here, from the values at these points, I don't need this point. From the values at these points, I want to go here. Okay, I want to calculate this, the values of temperature at these points at that time. Okay, as you can see, and as we discussed last time, for any point, if I want to calculate the value, let's say here, at some I, suppose this is my point I. So this would be TL plus T1I. That depends on this point, T0I, T0I minus 1, T0I plus 1. So these 3 points provide information to calculate this guy. Because as you can see, here we have at L, I have the point I have the point I plus 1, and I have the point I minus 1. So these 3 points contribute to calculation of 1 point. For example, this point, the first interior point, I will need information here, which is provided by the boundary condition, the information here, and the information here. For the last interior point, this guy, again, I need the information from this point, and from this boundary point. And this is how you evolve in time. This is how you evolve in time until you reach your final points that you need. Okay, very good. So this general expression of PDEs as a system of ODEs, basically here we are expressing PDE as a system of ODEs. That methodology, that kind of perspective is called method of lines. Method of lines. Method of lines. Okay, so in other words, again, solving this, considering this as a system of ODEs, we are applying explicit Euler method, okay? So we are applying here explicit Euler method in this discretization. If you look at it as a system of ODEs, So as you know, explicit Euler method has some issues of stability, right? Sometimes it can be stable, sometimes it may not be stable, okay? Just to remind you, we did this very simple analysis a few lectures ago for this very simple ODE. Let's say that we have an ODE of this form is equal to minus AY, where A is a constant which is larger than 0. This system is stable only if you use H, which is smaller than 2 over A. Otherwise, the numerical solution with explicit Euler's method will not be stable, right? The same thing applies here. In certain situations, it can be stable. In certain situations, it may not be stable. Namely, if delta t is smaller than 1 over 2 delta x squared over k, in this case, we have our numerical solution is stable. Okay? Or we can call this guy lambda for shorter notation. So this corresponds to lambda smaller than 1 over 2. Okay? If you call this guy lambda, this condition translates to lambda smaller than 1 over 2. Okay? This is for stability and convergence. Okay? The same way here, when we used h, which is roughly equal to 2 over a, roughly at the threshold of stability, in that case, we got oscillatory solution. Similarly, if we use lambda of the order of 1 over 2, we get a solution which is oscillatory. In order to get non-oscillatory solution, we need to use significantly smaller lambda, which is smaller than 1/4. And there is an indication that truncation error will be minimized when we use lambda equal to 1/6. Okay, so when we discussed this equation a few lectures ago, we also mentioned that implicit Euler method is unconditionally stable. No matter which h we use, which step size we use, we always get stable solution. The same story applies here. Actually, here, now let's come back here. Here, instead of using this kind of explicit method, explicit Euler method, we can actually apply implicit Euler method. How we can do that? So let's remind ourselves of explicit Euler method and implicit Euler method, and let's try to come up with an implicit method for this equation, or for this equation, okay? Okay, so just to remind ourselves, let's look at this ODE. dy dx, very simple ODE, is some f at x and y. So explicit Euler method has this form. yi plus 1 is equal to yi plus f of xi, yi multiplied by h. Implicit Euler, on the other hand, is given by the following formula. yi plus 1 is equal to yi plus f at xi plus 1, yi plus 1 multiplied by h. Okay, so that's the difference between Euler's explicit and implicit Euler. Here we have xi, yi. Here we have xi plus 1, yi plus 1. All right, so we said that this is explicit Euler method. In order to get implicit version of this equation, what shall we change here? What shall we change in order to get implicit Euler method? Instead of L, we need to get L plus 1. Very good. So implicit method here then would correspond to the following formula. TL plus 1 I is equal to TLI plus that term K second derivative of t with respect to x at L plus 1 multiplied by delta t. Okay, so we need this guy at L plus 1. So at L plus 1, we just put L plus 1 here, L plus 1 here, and if we put everything together, we should arrive at the following equation. Okay, so I put this guy here, and after some transformation, I arrive at the following equation: minus lambda, where lambda is this guy, is this term, ti minus 1, L plus 1, plus 1 plus 2 lambda, ti L plus 1, minus lambda, t L plus 1, I plus 1 is equal to ti L. I arrive at this equation. This is an implicit equation, right? Now we have to solve system of equations. So I have to apply this equation for every interior point, I ranging from 1 to m. If I do that, I get a system of m, m algebraic equations. Equations for T1, T2, and up to Tm, which are all of my unknowns, and that's what I am looking for. All right, okay. L plus 1 here, of course, L plus 1, L plus 1, and L plus 1. Okay, if I want to go at every time step, then at every time step, I have to solve a system of m linear algebraic equations. As you can see, this system is a tridiagonal. And that's the reason we actually learned the tridiagonal systems a long time ago, right? One of the reasons is to solve an equations of this form. This system, advantage of this system is that it is unconditionally stable because it's an implicit method. Okay, what is the disadvantages of this method? One disadvantage of this method is that it's first order in time. Okay, so this formula is the first order in time. Okay, global error, time error will be of the order of delta t. The same story is here. This is also first order in time. This formula is a first order in time formula, right? So our space discretization and time discretization is different here. My space discretization is what is the order here? What is the order here? I use this formula for space discretization. What is the order here? It's a second order formula, right? Error here is proportional to delta x. Here error is proportional. Here error is proportional to just delta t, first order. So you see drawback here. Drawback is here, or weak link, so to say. Here is in where time discretization, because time discretization is first order, and we use space discretization, which is second order. This is a second order formula. So if you want to improve the accuracy, we have to use a second order, for example, right? So instead of first order, simple error, we can use a second order method. Like, for example, what are the examples of second order methods? Hohen's formal method, right? Midpoint method. If you want higher order, you can also use higher order. For example, fourth order Runge-Kutta. Here. In the case of implicit, you cannot directly apply higher order explicit formulas, which we discussed. But there are other ways of achieving higher order here. Other ways of achieving higher order here. Okay? So I'm going to describe one method, which is called Crank-Nicolson method. Okay, so I want to describe method called Crank-Nicolson method. So this is an implicit method, like this method. But the advantage of this method as opposed to this method is that here I have second order in time discretization. Here I have only first order in time. How can I achieve that? I can achieve that in this very smart way, Suppose this is my time and space diagram. This is my t-axis, this is my x-axis. Suppose this is time step TL, and suppose this is time step TL plus 1. Okay? So I have the information here. I solved it for this guy. So I have the information at TL, which means I have TL I at every I. I want to go to L plus 1. I want to find these guys. Okay. The idea of the Crank-Nicolson method is very simple, but also very clever. Okay, what I want to discretize this equation in time in the midpoint. How? In the following way. Second derivative of t with respect to t at L plus 1 over 2 in the midpoint. I want to estimate at this guy at L plus 1 over 2. At I will be, now I can use a centered formula. Before I used forward formula, that's the first order. Now I can use the centered formula in space also, in time also, sorry, which is T L plus 1 at I minus T L I divided by delta T. This is the centered formula. Do you agree? So the error will be of the order of delta T squared. This is the second order formula. Because I'm using it, I'm calculating it here, so I need to use information here and divided by delta T. That's why it's a centered formula. Very good. Now, next thing is to calculate this guy in the center. And there, the trick is the following. So second derivative of t with respect to x at L plus 1 over 2, and I is very simple. We calculate the same thing here and take the average. Okay? So 1 over 2, this guy at this point plus the same guy at this point, average of these two. Okay, so here it will be TL I plus 1 minus TL I with 2 plus T I minus 1 L over delta x squared plus in the next point in time T L plus 1 I plus 1 minus 2 T L plus 1 I plus T L plus 1 I minus 1 divided by delta x squared. Okay, average at L and L plus 1, average of these two quantities. So then this one, I say this one is equal to that guy, this guy and equal to that guy. Okay. If I do that, I get the following very simple equation, system of algebraic equations. Minus lambda t L plus 1 I minus 1 plus 2 t1 plus lambda ti l plus 1 minus lambda ti plus 1 l plus 1, and all of that is equal to lambda ti l I minus 1 plus 2 1 minus lambda ti l plus lambda ti l I plus 1. Lambda is again the same quantity, which is t delta t k divided by delta x squared. Okay, now again I get a system of algebraic equations for interior points. System of m algebraic equations for m values of t l plus 1 I, where I ranges from 1 to m. Okay, at each time step, when I go from l to l plus 1, I have to solve this system. Again, this system is a three-diagonal. I apply this efficient algorithm, Thomas algorithm, which we discussed some time ago. All right, very good, very good. That's it for the day.